Today we shall study about magnetostatics. Theory of magnetism. Weber was the first to advance the molecular theory of magnetism to account for the well-known magnetic effects. Later it was developed by Ewing. According to this theory, the molecules of a magnetic substance, whether magnetized or not, are complete magnets. The elementary magnets are sometimes called Weber elements. In an unmagnetized piece of iron, the molecules are arranged in groups, each group forming a stable magnetic system and producing no external magnetic action, as shown in figure 1. Now, the third point is on subjecting the magnetic material to external magnetizing field. The piece is magnetized and its behavior can be well understood by examining the magnetization curve figure 2. When the magnetizing field is small, each member of the group is deflected towards the magnetizing field without rupturing the group formation. If the magnetizing field is withdrawn, each member returns to the original direction and there is no magnetization left. This is represented by the portion OA of the curve when magnetic induction is proportional to the magnetizing field and there is no appreciable hysteresis loss. Now, when the magnetizing field is further increased, a second stage of magnetization is reached when the individual component of each group of molecules get more and more deflected until rupture is caused in some groups. The molecules thus broken asunder from the groups rearrange themselves and develop new groups which are more nearly aligned in the direction of the magnetizing field. This state corresponds to the part AB of the curve and is characterized by a rapid increase in the magnetic induction. Now, with the magnetizing field, figure 2. Now the third, when all the molecules have aligned themselves in the new group, a condition of saturation is attained, represented by the part C of the magnetization curve. These three stages are not sharply distinct from each other, as shown in figure 3. The molecular alignment in presence of a strong magnetizing field shown in figure 3. Now, after the attainment of the saturation, if the magnetizing field is gradually lessened, the intensity of magnetizing decreases as the magnetizing field is reduced but does not become zero even when the magnetizing field is completely removed. This is due to the fact that closed molecular rings are not formed when the magnetizing field is reduced. Hence, a considerable amount of residual magnetism, OD, as in figure 2, is still left in the iron even when the magnetizing field is completely removed. Thus, the magnetic induction lags behind the magnetizing field. This phenomenon is called hysteresis. It is easily seen that the effect of hysteresis would lead to a loss of energy dissipated in the form of heat, because each time the individual molecules get separated from a group, they set a vibrational and the corresponding kinetic energy is transformed into heat. Now, the fourth number is when all the molecular magnets have been aligned in the direction of magnetizing field, it produces a preponderance of the north poles at one end and and of the south poles at the other end, and the piece begins to exhibit a strong magnetic property in a magnet, in a magnetized bar. The central portion of the magnet does not show any magnetic property as there are no free poles. The attraction is not confined to the end face only, but extended to a small region near the ends, showing the existence of a lateral magnetization, which can be explained on the existence of the molecular magnets. Near the ends, we have similar free poles, and the molecular chains are bent towards the sides because of lateral repulsion between the adjacent chains in conjunction with the tendency of the lines of force to contract longitudinally.